Welcome everyone. Sorry for the delay. I had some meeting in my department. That's why I had to go. So I will start the class. So welcome everyone to the live interactive session number 5 for the course Mechanics of Fiber Reinforced Polymer Composite Structure. Today I am going to discuss some sample problems which will be useful for solving the questions of assignment number 5. And my name is Ananya Mandal. I am one of the TAs of this course. So let's start with the first question, that which of the following is or are true? The options are A. Presence of void in a FRP composite leads to reduction in shear strength and stiffness. Option B. Presence of void in a FRP composite leads to increase in shear strength and stiffness. Option C. Presence of void in a FRP composite leads to reduction in compressive strength and stiffness. Or option D. Presence of void in a FRP composite leads to increase in compressive strength and stiffness. So here we are talking about void. So let's see what is a void. So void is the unintended third phase present in nearly all composite materials. Voids are unoccupied pores in the material, essentially empty space filled with gas instead of solid material. Typically, they are the result of imperfections in the manufacturing process and are seen as undesirable because they can reduce the mechanical properties and therefore the lifespan of the finished composite. As defects, they can act as crack nucleation sites, and following propagation of said cracks can cause unpredictable behavior, even catastrophic failure in the composite. So from the definition of void, you can see that the voids are some empty spaces in the composite, which can lead to decrease in the mechanical properties of that composite, and in further cases can lead up to failure of the composite. So from that definition, you can see which of the following options are the true ones. So the correct options are option A, that the presence of void in FRP leads to reduction in shear strength and stiffness, and also option C, that it can reduce the compressive strength and stiffness. So any type of mechanical properties will get reduced if there is any void inside the composite. The next question is that in a unidirectional glass epoxy lamina, the Young's modulus and Poisson's ratio of glass fiber are given, where EF equal to 82 gigapascal, mu F equal to 0.24 respectively, and the Young's modulus and Poisson's ratio of epoxy are EM equal to 3.6 gigapascal and mu M equal to 0.3 respectively. The fiber volume fraction is 58%. So the question is that what will be the longitudinal Young's modulus of the lamina in gigapascal? So as sir already taught in class, uh, uh, when we are considering fiber volume fraction, so according to what kind of load we are calculating, there are equations for solving including the fiber volume fraction. So when we are talking about the longitudinal Young's modulus, so we are considering that the load is along the direction 1. Load is getting in direction 1. So we will equate the force that will be given by the fiber as well as the matrix, and it will be equal to that of composite. So when we are doing the force balance of the fiber and matrix equal to composite, force can be written as the as the stress multiplied by the area, and stress can be further written as modulus into the strain. Now, considering that the strain will be equal if there is a perfect bonding between the matrix and the fiber, so what will be left at the end will be this equation, which is equating the modulus of the composite with respect to the area of the fiber, area of the matrix, area of the composite, and the modulus of the fiber and matrix. Now, as we know that the ratio of the area of the fiber and the composite can be also written as the ratio of volume of the fiber and volume of the composite. Similarly, for area of matrix and area of composite, that will be volume of the matrix divided by volume of composite. Now, this volume ratio can be known as the volume fraction. So, the volume of the fiber divided by composite will become the fiber volume fraction, and that of matrix will become matrix volume fraction. So, and also the sum of the volume fiber volume fraction and matrix volume fraction is equal to 1. So, from that we can get the values of VF and VM. So, in the question, we have to find the longitudinal Young's modulus E1. So the equation will be equal to EF VF plus EM VM. So the EF value is given 82 gigapascal and the EM value is given as 3.6 gigapascal. And also the fiber volume fraction is given 58%, that will be 0.58. So from that minus by 1 we can get the matrix volume fraction, that will be 0.42. So from all these values, when we will put the values in this equation, we can get the longitudinal length modulus as this. That will come as 49.07 gigapascal. So the derivation how to find this final equation is already shown in the class, and this is a example how by putting those values you can get the final modulus of the whole composite by knowing the modulus of the elements of that composite and also how much fraction of that composite is having the fiber and the matrix. And the next question, for the same given data, they are asking the transverse Young's modulus of the lamina is. So when we are considering the transverse Young's modulus, then we say that the load is along the direction 2. So if there is a load in this direction, so the total change in length of the composite will be equal to the change in length of the fiber plus the matrix. So from this, the change in length is equated to the actual thickness of that composite and the strain of the composite. As strain is equal to the change in length divided by the initial length. So when we will equate it with respect to strain, and the strain is also is equal to stress divided by the modulus. When we will put those things in this equation, considering that the stresses are equal, so we will get this as the final equation with respect to the transverse Young's modulus. Now, here you can see there is a ratio of the thickness of the fiber with respect to composite and matrix with respect to composite. As we already know that this ratio of thickness as well as area can also be equated to volume. So it will also give you the volume fraction. So when we'll put the concept of volume fraction in that, it will become that the 1 by E2 will be equal to Vf by Ef plus Vm by Em. So this is the form of equation first for when they have asked transverse Young's modulus. So in the previous one they were asking longitudinal. So longitudinal comes equation is like this, whereas for transverse the equation becomes this. So these are the two kinds of equations which considers the engineering constants and the volume fraction to find the final engineering constant of the composite. So putting the this equation in use and the values already given of EF and EM and the fiber volume fraction from which we can get the matrix volume fraction, we can get the final value of E2. So this will be the transverse Young's modulus. And our next question, they are asked about Poisson's ratio of the lamina with the same given data. So similarly, the derivation of the final equation of the Poisson ratio of the composite was done as already shown in the class. I will not go back to it. So from all this derivation, the final equation for calculating the Poisson ratio is kind of similar like that of the longitudinal modulus. So we will put the value of Poisson ratio of the fiber, the matrix, and the volumetric, the fiber volume fraction and matrix volume fraction in this equation. From that, we can get the value of the Poisson ratio. So this is the value of Poisson ratio 0.265. Next question, they are asking that for the lamina, the value of the element Q11 in the reduced stiffness matrix is. So this is back to the original things back to the macro mechanics that we have already studied before. So we have already studied about the reduced stiffness matrix, how we get this reduced stiffness matrix, and what are the relation of those components of the reduced stiffness matrix with the engineering constants. So here you can see from the previous classes, the relation between the engineering constants and the different components of the stiffness matrix and or the reduced stiffness matrix. So from this equation, they are asking Q11. So this is the equation of Q11, which is equal to E1 by 1 minus mu12 mu21. So E1 value we already calculated from this in this question. The longitudinal Young's modulus E1 we got. Mu12 value we got from the previous one. This is mu12 value. And there is already an equation relating mu21, mu12 with E1 and E2. So E2 value we already got from this question. So by using the data of the previous three questions, E1, E2 and mu12, we can get the value of mu21, and putting that value here, we can get the value of Q11. So that will come out to be 49.65 gigapascal. Okay, so these were these three values E1, E2, mu12 we can get from the engineering from the different values of the matrix and fiber. the different properties and adding them along with the how much fiber and matrix is there in that composite, we can get the final value of these properties of the composite. We can use it for making the like reduced stiffness matrix for the whole composite like this. Now next question is question number 6, that the fibers are arranged in a square array in a unidirectional glass epoxy lamina having a volume fraction of 58%. The in-plane shears moduli and Poisson's ratio of the circular glass fibers are GF equal to 30 gigapascal, mu F equal to 0.24 respectively. And those for epoxy are GM equal to 1.2 gigapascal and mu M equal to 0.3 respectively. Using the Helfin-Psi equations, the in-plane shear modulus of the lamina is, and we have to find the value in gigapascal. So, as I told in the class, that initially when we are trying to find the longitudinal values, then initially when we are trying to find the longitudinal values, those equations were valid. The equations that we previously used in the question, so those kind of equations were valid to find the transverse for the longitudinal values. But when they tried to solve those equations for the transverse values, they saw that those values were not very equal to the experimental values. So at that case, some semi-empirical formulas like Helfin-Psi was used to find the transverse uh, uh, properties. So one of these is example is this question where they are asking, by using the Helfin-Psi equation, we have to find the in-plane shear modulus of the lamina. Now the equation for the Helfin-Psi is this, where M is the properties of the composite, M is the properties of the matrix, and uh, eta is the reinforcement factor, which gives the properties of the reinforcement use. And VF is the fiber volume fraction. And this eta value, this is the equation for the eta value. Now, one of the unknown property here is the zeta. So, zeta we have to always remember that the zeta values can be two types, one or two. Now, also according to the geometry of the fiber, eta value will be either 2 or 2 into a by b, that already sir has taught. But also when we are talking about shear modulus evaluation, that time zeta value we have to take as 1. And when we are talking about the transverse modulus evaluation, that time we have to take zeta value as 2. So while solving the questions, make sure to understand, see what is asked in the question. Either they are talking about the shear modulus or the transverse modulus. So for whenever we are talking about shear modulus, we have to take the zeta value as equal to 1. And for transverse modulus, we have to take the zeta value as 2. So here the equation is already given. We have to find the in-plane shear modulus. So first we have to find the value of this eta. It is equal to MF by MM. So MF is the property of the fiber divided by property of matrix minus 1. So here the shear modulus of the fiber and matrix is already given. We will put those values, and the zeta value will be equal to 1 because we are considering the shear modulus evaluation. So that will come value as 1. So after putting this value, we can get the value of eta. Now we have to find the M. Here M is the shear modulus and MM is the shear modulus of the matrix. So putting that values, as we know the value of zeta, eta, and VF is given as 58%, that will be 0.58. Putting those values, we can finally get the in-plane shear modulus of the lamina, the whole composite, as 3.965 gigapascal. Uh, so the next question is that a circular cross-section fibers are arranged in a square array in a unidirectional glass epoxy lamina having a volume fraction of 65%. The Young's modulus and Poisson ratio of the circular glass fibers are given, that is EF equal to 80 gigapascal, mu F equal to 0.24 respectively. And those for epoxy are EM equal to 3.2 gigapascal and mu M equal to 0.3 respectively. If E2 mm is the transverse Young's modulus evaluated using mechanics of material approach, and E2 HP is the transverse Young's modulus evaluated using the Helfin-Psi model, then the ratio E2 HP E2 mm is. So here basically they're comparing the two approaches for solving the transverse properties. So the two approaches are mechanics of material approach and the Helfenstein method. So mechanics of material approach, what we already did in this question number 3. Here we have the direct equation to find the transverse Young's modulus, where we will use the volume fraction, fiber volume fraction and matrix volume fraction, and the Young's modulus of the fiber and matrix in this equation. So from that we can get this E2 value. So we used that equation here and found the E2 value by this mechanics of material approach, come at as 8.51 gigapascal. Now comes the Helfenstein model. So as I already told, when we are considering transverse modulus, we have to take the zeta value is equal to 2. So we took the zeta value equal to 2. The first step was to find the value of eta. For eta, the equation already discussed that we need the properties of the fiber and matrix and the value of zeta. So putting those properties in the equation of eta, we will get the value of eta is 0.8889, and then we have to use this equation to find the final property of the composite, here signified by m. So we will put the values in this equation. And then finally we can get by Helfenstein method the value of E2 as 16.34 gigapascal. So you can see there is so much difference between using the Helfenstein model and the mechanics of material approach. So now we have to find the ratio. So by putting the we have to find the ratio by dividing 16.34 to 8.51, and we can see the ratio between these two methods is 1.92. So this is what it was. So this is what I discussed, that how the mechanics of material approach was not giving a good value equal to the experimental values. That's why we went for the semi-empirical methods like Helfenstein model. So next we are going to talk about this concept. What is the um, critical volume fraction and the minimum volume fraction? So the definition says that once the fibers have broken, the stress that the matrix can take alone is given by sigma m ultimate into 1 minus VF. So only if this stress is greater than the ultimate tensile strength is it possible for the composite to take more load. The volume fraction of fibers for which this possible is called the minimum fiber volume fraction VF. And this is the equation for finding the VF value. Whereas VF minimum. Whereas it is also possible that by adding fibers to the matrix, the composite will have lower ultimate tensile strength than the matrix. In that case, the fiber volume fraction for which this is possible is called the critical fiber volume fraction VF. And this is the equation for fiber volume fraction, critical fiber volume fraction. So what are these two talking about? So the first one, the minimum fiber volume fraction is when uh, once the fibers are broken, the stress that the matrix can take alone, if this stress is greater than the ultimate tensile strength, then the composite can take more loads. So that volume fraction of that fiber will be the minimum one. Whereas by adding the fiber to the matrix, the composite will have lower ultimate tensile strength than the matrix. In that case, the fiber volume fraction for which this is possible will be called the critical fiber volume fraction. So now let's see some questions on that concept. So the question is that in a unidirectional glass epoxy lamina, the Young's moduli and Poisson's ratio of the fiber and matrix are given as EF equal to 80 gigapascal and mu F equal to 0.24 respectively. And those for epoxy are EM equal to 3.2 gigapascal, mu M equal to 0.3 respectively. Ultimate strengths of the fiber and matrix are given. So the stress tensile stress of the fiber ultimate and the compressive strength of the fiber is given as 1600 megapascal, and the tensile strength, ultimate tensile strength of the matrix is 70 megapascal, and ultimate compressive strength of the matrix is 100 megapascal. So we have to find the critical volume fraction. So this is the equation for critical volume fraction, which is equal to the ultimate stress of the matrix minus sigma m ultimate 70 megapascal minus EM value is given 3.2 gigapascal multiplied by eta f. Stress value. Okay, sorry. So this is the strain of the ultimate strain of the fiber. So the critical volume fraction is equal to strength of the matrix ultimate minus the strain of the fiber ultimate multiplied the modulus of the matrix divided by the stress of the fiber ultimate minus strain of the fiber ultimate into the modulus of the matrix. So we have all these values given to us. We will put those values and we can get the critical volume fraction, that is 0.391%. For the next question, they have asked with the given values, what will be the minimum volume fraction? So to find the minimum volume fraction, this is the equation. So all these values, the matrix stress ultimate, the fiber strain ultimate, the modulus of matrix, and all these values are already given in the question. We will put those values and we can get the minimum volume fraction as 0.3736%. So we all are direct equations we can use, as all the data are already given in the question.
VM. Now, in order that this does not happen, that means when the fiber breaks, the composite is
So we can get the minimum volume fraction. The last question is that in order to ensure that the addition of fibers to the matrix leads to tensile strength of the composite more than that of the matrix, so what should we use? The options are A, the fiber volume fraction should be more than critical volume fraction. The fiber volume fraction should be less than critical fiber volume fraction. The fiber volume fraction should be more than minimum fiber volume fraction, or the fiber volume fraction should be less than minimum fiber volume fraction. So to ensure that the addition of fibers to the matrix leads to tensile strength of the composite more than the matrix. So for that condition, we have to consider the critical fiber volume fraction. As the definition of critical fiber volume fraction, they said that by adding the fiber to the matrix, the composite will have uh, a lower ultimate tensile strength than the matrix. At that time, we considered the critical fiber volume fraction. So to have the ultimate tensile strength uh, of the composite more than that of the matrix, as critical fiber volume fraction talks about the tensile strength of the matrix. So if we want the composite to have tensile strength higher than the matrix, then we have to consider the critical fiber volume fraction. So from that definition, we can say that the fiber volume fraction of the composite should be higher than that of the critical fiber volume fraction. So that will be the answer. So any doubts in the question?
failed. That means the matrix cannot take further load.
So any doubts in the questions that I discussed or anything from the what sir had taught or the recent assignment you can discuss. Yes, sir. You raised your hand.
This session is over.
Yes, sir. Sir, are you saying something because you're muted?
Ma'am, you're dealing with assignment number 5 week. Is this session over?
Yes, sir. Like I discussed all the sample questions that would be helpful for solving the assignment number 5. But if you have any doubts regarding the assignment number 5, and then we can discuss.
Oh, I came late, so I'm not sure. Yeah. No problem. Later I can watch the video. No problem.
Uh, okay, sir. This video will be uploaded in YouTube by tonight. So, and if you have doubts regarding that, and then you can write it in the comments also. I can reply to that.
Okay. Okay.
Yes. Okay, then if you have no doubts, then like from my side, I revised it once. But if you want me to like explain the questions again, then you can say tell. Otherwise, I will be here till 8. So if you have any other doubts, we can discuss, or you can leave if you have no doubts. Yes, Hari Krishna. Actually, you are late today in the class.
Yeah, ma'am. Yeah. Came
Uh,
just now, ma'am.
okay, so do you
Ma'am,
want me to
is the
repeat?
session over? No problem. No, ma'am. No problem, ma'am. I'll later I can see the videos, ma'am. No problem.
Okay,
Ma'am,
and
is the session over? I have few doubts on the last assignment. One, can we proceed on it?
okay, yeah, I have discussed this one. So
No,
if you have any
once,
doubts, we can discuss.
no, ma'am. Once if the session is over, then we can start off it, ma'am.
This session is over. Everyone who came, I discussed the sample problems for assignment 5. So if you have any doubts in assignment 5, we can discuss now.
Okay, ma'am. Just a minute. Ma'am, shall I share my screen now?
Okay, you can share.
Ma'am, here in problem number 3,
Yes.
ma'am, in problem number 3, in total gas, I have listened, you have said, I have also solved the same issue, ma'am, but the answer I got also same like yours. But it was called not safe, and the mode is only share only, ma'am. But here it was showing it was a transfer tensile, ma'am. How it is?
Um, okay, let me try like solve it and
Ma'am, this one and one more thing, ma'am. One more thing. Next and mm, on problem number 4, ma'am. I have solved in the same issue. It was in uh, in in problem solving also it will come minus. Same I have did minus 3.64, but it was showing again plus 34.2, ma'am. Please help with these two, ma'am. And also final thing, problem number 8, ma'am. Problem number 8. You have clearly said if the lamina is fully retained, then the the this value is 0. But here the values comes, ma'am. I have taken notes regarding your problem statement session. I have solved using this, but I have placed the same answer, but showing here also some wrong answers, ma'am. Can you please help me with this, please?
no, tau xy will not be equal to 0 for a restraint. Restraint means the strain will be equal to 0. Even the question that I discussed, tau xy value was there.
No, ma'am. No, ma'am. I can check you. Tell you, ma'am.
Yeah, tau xy will be 0 because there is no alpha xy. So if there is no alpha xy, so in the matrix, the Q matrix, only Q66 value will be there. But when you will do it with tau, as there is no strain in shear, that's the shear strain, that's why it should be equal to 0. I don't know why you are not getting this answer. Can you do one thing? In the discussion of this, there is a discussion portal for this course. So it will be better if you ask this question in the discussion panel because then sir will be able to see the questions and sir will directly answer. Or if there is any live session that been given for sir, then he can also come and talk to you about this problem. Because according to my
But what
calculation,
I'm
I
say, ma'am, but what I'm did is right only, na, ma'am. As per your problem solution, I have solved this issue.
yes.
But okay, ma'am. Then one more thing for this also, ma'am. Mm,
Yeah. According to how it should be solved, it should be tau xy should be equal to 0. I don't know why they are not giving this different answer. Did anyone else had the same problem with this assignment? Anthony, Shashi, if anyone can answer, if they solved the same thing, then we can discuss. Okay. Uh, yeah, according to how to solve from sir's class and everything, it should be equal to 0. I don't know why. Okay, can you scroll it up to question number 3 and 4? Let me see those also.
yeah, ma'am. Yeah, ma'am. Yeah, exactly this one, ma'am. For question number three, the lamina is not safe and the mode of failure is shear, ma'am.
Yes, in this one, you can see the ultimate values of the shear. It is coming out of that range. That's why it showed that the failure is shear. So what is the value of
You
like
have, ma'am.
sigma 1, sigma 2 and tau 1, 2 that you got in that question?
Yeah, ma'am. Yeah, ma'am. I get that paper, ma'am. I missed that paper. But it was coming same like this, ma'am. First one value is positive, next two is negative. The same like this only it was also came, ma'am.
But did those values staying within the range that you have to see? Like even if it like second value tau sigma 2 if you're getting as negative, it should lie between the minus of the compressive strength in tensile and positive of the tensile strength of transverse. So you have to see this range. The second option you see. Like here in the screen, you can see the
Okay.
ultimate compressive strength in transverse. It is 275. So minus 275 to positive 40. It was lying between that.
Yeah, okay. As you said, that if the value is more different, then it may not be in limit, so it comes under transfers. I understand this, ma'am.
You understood the range between which the value should stay. So if it is not in that range, then that will be
Yeah,
the
yeah,
failure.
yeah, yeah, ma'am.
And And what about question number 4?
Yeah, ma'am, next one more thing. Yeah. Ma'am, this question number 7 over here. Exactly question number 7, ma'am. I have solved the issue, but I am getting a positive value here, ma'am. But answer it was showing negative value. This is a very minimum mistake. That's why I lose the maximum points for this, ma'am.
Which option did you choose?
I have
D.
choose the option number D.
Okay, negative.
But the correct answer was option number C, ma'am.
So, 1 minute, cos 60. See, I think when you did the transformation matrix, so transformation matrix you have to use in the seventh one. So in the shear value, so it will be
That means the strength, the longitudinal tensile strength of the fiber must be more than this. So if we put
cos square, cos 60 square minus sin 60 square. So in that way it will be negative. So that's why you got negative, right? So why it is so important? That way it is giving netting negative. So the transformation matrix that you have to use to change it from this principal axis to global axis, the material axis to global. So you multiply it with the transforming matrix, right? With cos and sine square, sine of the theta.
Mm.
Wait 1 minute. I will share my screen. I can explain this one. Can I share?
Ma'am, for the same problem, it was came positive only, ma'am.
No. If you see cos square, cos 60. What is the value of cos 60? 1 by 2, and cos and sine 60 will be equal to root 3 by 2. So the value of root 3 by 2 will be higher than so cos 60 value will be higher than sorry, sine 60 will be higher than cos 60. So the equation is cos 60 square minus sine 60 square. So that is coming as negative. So when you will multiply it with negative, you will get the shear value is negative only. Wait, I will. Can you stop presenting? I will present my screen.
Yeah.
So this is where you are having the problem. So see the transforming matrix. Here the in the question that you have solved, the angle they have given is 60-degree, right? So
Yes, ma'am.
this term is what causing the negative in the question that is given in that assignment and not and positive here. So cos square of 60-degree minus sine square of 60-degree will be negative. So this value here will be minus.
Mm.
And when you will multiply it with, so will it come like that? Can you check once?
Okay, ma'am. I'll check on it. Yeah.
I think in the transforming matrix only there is negative term coming because of that value will be negative, but check it once by solving. Any other doubts, Hari? Hare Krishna. And your email
Mm,
ID, I tried, but I couldn't send mail on that one.
okay, ma'am. Ma'am, that's what I'm asking, ma'am. Some any step-by-step problem solving, it will be useful for us, ma'am. Very long time we have used this matrix. Nowadays, we are going for squeeze casting composites like that, ma'am. So we are well away from this those matrix solving session. So if one or two problem we get any step-by-step solved, it means it will be useful to again solve and not making minor mistakes on it.
Uh,
Do
actually,
you have any related notes to have, ma'am?
no, I don't have any notes. Like, I do directly from questions. But sir teaches in class also. Some examples.
Yes, ma'am. Yes, I have seen, ma'am. Yes, I have seen, ma'am.
Next class, I think there will be ABBD matrix and all. Those were like more bigger matrix. So I will try to include some step by step like calculation if I am able to in the next class because that will be more difficult. I will try to include it myself.
Okay, ma'am. Yeah, ma'am. Okay.
क्या हो रहा है?
Okay, then I will end this session here. Okay, thank you.
Um,
Ah, yes.
um, Ma'am, for today's session, today night I will check out the past videos. I'll solve this problems and send you mail. Ma'am. Can you check it tomorrow? It is right or wrong?
Yeah, but I tried to send you mail, but your mailing ID is not working. I don't think you got my mailing ID also.
Now, yes, but today I got your mail ID, ma'am. Um, I can text you, ma'am, if you don't, ma'am.
Uh, did you get my mail?
Yeah, ma'am. Yeah,
Okay, okay,
it
then you
was
send it in my mail then.
um, 39@gmail.com. It is right, ma'am.
Ah, okay, we can send it.
Please see morning and reply it, ma'am. Thank you. Yeah,
Okay, you can send them back. Okay, thank you.
yeah, ma'am. Thank you.